Cherenkov radiation, also known as Vavilov-Cherenkov radiation, is electromagnetic radiation emitted when a charged particle passes through a dielectric medium at a speed greater than the phase velocity of light. In that medium, the characteristic blue glow of an underwater nuclear reactor is due to Cherenkov radiation. It is named after Soviet scientist Pavel Alexeyevich Cherenkov, the 1958 Nobel Prize winner who was the first to detect it experimentally. A theory of this effect was later developed within the framework of Einstein's special relativity theory by Igor Tamm and Ilya Frank, who also shared the Nobel Prize. Cherenkov radiation had been theoretically predicted by the English polymath Oliver Heaviside in papers published in 1888–89. Physical origin. While electrodynamics holds that the speed of light in a vacuum is a universal constant, the speed at which light propagates in a material may be significantly less than c. For example, the speed of the propagation of light in water is only 0.75 c. Matter can be accelerated beyond this speed during nuclear reactions and in particle accelerators. Cherenkov radiation results when a charged particle, most commonly an electron, travels through a dielectric medium with a speed greater than that at which light propagates in the same medium. Moreover, the velocity that must be exceeded is the phase velocity of light rather than the group velocity of light. The phase velocity can be altered dramatically by employing a periodic medium, and in that case one can even achieve Cherenkov radiation with no minimum particle velocity, a phenomenon known as the Smith-Purcell effect. In a more complex periodic medium, such as a photonic crystal, one can also obtain a variety of other anomalous Cherenkov effects, such as radiation in a backwards direction. As a charged particle travels, it disrupts the local electromagnetic field in its medium. In particular, the medium becomes electrically polarized by the particle's electric field. If the particle travels slowly, then the disturbance elastically relaxes back to mechanical equilibrium as the particle passes. When the particle is traveling fast enough, however, the limited response speed of the medium means that a disturbance is left in the wake of the particle, and the energy contained in this disturbance radiates as a coherent shock wave. A common analogy is the sonic boom of a supersonic aircraft or bullet. The sound waves generated by the supersonic body propagate at the speed of sound itself. As such, the waves travel slower than the speeding object and cannot propagate forward from the body, instead forming a shock front. In a similar way, a charged particle can generate a light shock wave as it travels through an insulator. We define the ratio between the speed of the particle and the speed of light as the emitted light waves travel at speed. The left corner of the triangle represents the location of the superluminal particle at some initial moment. The right corner of the triangle is the location of the particle at some later time t. In the given time t, the particle travels the distance, whereas the emitted electromagnetic waves are constricted to travel the distance. So, note that since this ratio is independent of time, one can take arbitrary times and achieve similar triangles. The angle stays the same, meaning that subsequent waves generated between the initial time t equals 0 and final time t will form similar triangles with coinciding right endpoints to the one shown. Reverse Cherenkov effect. A reverse Cherenkov effect can be experienced using materials called negative index metamaterials. This means, when a charged particle passes through a medium at a speed greater than the phase velocity of light in that medium, that particle will radiate from a cone behind itself, rather than in front of it. One can also obtain such reverse cone Cherenkov radiation in non-metamaterial periodic media. Arbitrary Cherenkov emission angle. Cherenkov radiation can also radiate along arbitrary direction using a properly engineered one-dimensional metamaterials. The latter is designed to introduce a gradient of phase retardation along the trajectory of the fast-traveling particle, reversing or steering Cherenkov emission at arbitrary angles given by the generalized relation. Characteristics. The frequency spectrum of Cherenkov radiation by a particle is given by the Frank-Tamm formula. Unlike fluorescence or emission spectra that have characteristic spectral peaks, Cherenkov radiation is continuous. Around the visible spectrum, the relative intensity per unit frequency is approximately proportional to the frequency. That is, higher frequencies are more intense in Cherenkov radiation. This is why visible Cherenkov radiation is observed to be brilliant blue. In fact, most Cherenkov radiation is in the ultraviolet spectrum. It is only with sufficiently accelerated charges that it even becomes visible. The sensitivity of the human eye peaks at green, and is very low in the violet portion of the spectrum. There is a cutoff frequency above which the equation can no longer be satisfied. The refractive index varies with frequency in such a way that the intensity cannot continue to increase at ever shorter wavelengths, even for very relativistic particles. At X-ray frequencies, the refractive index becomes less than unity and hence no X-ray emission would be observed. However, X-rays can be generated at special frequencies just below the frequencies corresponding to core electronic transitions in a material, as the index of refraction is often greater than 1 just below a resonant frequency. As in sonic booms and bow shocks, the angle of the shock cone is directly related to the velocity of the disruption. The Cherenkov angle is zero at the threshold velocity for the emission of Cherenkov radiation. The angle takes on a maximum as the particle speed approaches the speed of light. Hence, observed angles of incidence can be used to compute the direction and speed of a Cherenkov radiation-producing charge. Cherenkov radiation can be generated in the eye by charged particles hitting the vitreous humor, giving the impression of flashes, as in cosmic ray visual phenomena and possibly some observations of criticality accidents. Uses: detection of labeled biomolecules. Cherenkov radiation is widely used to facilitate the detection of small amounts and low concentrations of biomolecules. Radioactive atoms such as phosphorus-32 are readily introduced into biomolecules by enzymatic and synthetic means and subsequently may be easily detected in small quantities for the purpose of elucidating biological pathways and in characterizing the interaction of biological molecules such as affinity constants and dissociation rates. More recently, it has been used to image substances in the body. Nuclear reactors. Cherenkov radiation is used to detect high-energy charged particles. In pool-type nuclear reactors, beta particles are released as the fission products decay. The glow continues after the chain reaction stops, dimming as the shorter-lived products decay. Similarly, Cherenkov radiation can characterize the remaining radioactivity of spent fuel rods. Astrophysics experiments. When a high-energy gamma photon or cosmic ray interacts with the Earth's atmosphere, it may produce an electron-positron pair with enormous velocities. The Cherenkov radiation from these charged particles is used to determine the source and intensity of the cosmic ray or gamma ray, which is used for example in the imaging atmospheric Cherenkov technique, by experiments such as Veritas, HESS, MAGIC and more recently by the extensive air shower experiment HAWC. Similar methods are used in very large neutrino detectors, such as the Super Kamiokande, the Sudbury Neutrino Observatory and IceCube, in the Pierre Auger Observatory and other similar projects. Tanks filled with water observe the Cherenkov radiation caused by muons, electrons and positrons of particle showers which are caused by cosmic rays. Cherenkov radiation can also be used to determine properties of high-energy astronomical objects that emit gamma rays, such as supernova remnants and blazars. This is done by projects such as STACEE, a gamma-ray detector in New Mexico. Particle physics experiments. Cherenkov radiation is commonly used in experimental particle physics for particle identification. If the momentum of the particle is measured independently, one could compute the mass of the particle by its momentum and velocity, and hence identify the particle. The simplest type of particle identification device based on a Cherenkov radiation technique is the threshold counter, which gives an answer as to whether the velocity of a charged particle is lower or higher than a certain value by looking at whether this particle does or does not emit Cherenkov light in a certain medium. Knowing particle momentum, one can separate particles lighter than a certain threshold from those heavier than the threshold. The most advanced type of a detector is the rich, or ring imaging Cherenkov detector, developed in the 1980s. In a rich detector, a cone of Cherenkov light is produced when a high-speed charged particle traverses a suitable medium, often called radiator. This light cone is detected on a position-sensitive planar photon detector, which allows reconstructing a ring or disk, the radius of which is a measure for the Cherenkov emission angle. Both focusing and proximity focusing detectors are in use. In a focusing-rich detector, the photons are collected by a spherical mirror and focused onto the photon detector placed at the focal plane. The result is a circle with a radius independent of the emission point along the particle track. This scheme is suitable for low refractive index radiators, i.e., gases, due to the larger radiator length needed to create enough photons. In the more compact proximity focusing design, a thin radiator volume emits a cone of Cherenkov light which traverses a small distance, the proximity gap, and is detected on the photon detector plane. The image is a ring of light, the radius of which is defined by the Cherenkov emission angle and the proximity gap. The ring thickness is determined by the thickness of the radiator. An example of a proximity gap-rich detector is the high-momentum particle identification detector, a detector currently under construction for ALICE, one of the 6 experiments at the LHC at CERN. In popular culture, the blue color of Dr. Manhattan in Watchmen may have been inspired by Cherenkov radiation.